values accumulate and in general do not satisfy a gap condition. Then in this talk, we are going to work with some keywords. We are going to analyze the control codes for boundary null controllability problem, and this is important. Also, we are to deal with coupled parabolic system, and this is also very important. We have systems in general which are coupled with a number less controlled than equation. And the third important thing is that we have eigenvalues that in general not satisfy a gap condition. And in fact, we can have a condensation of these eigenvalues. Well, I'm going to start with a first section. In this section, we are going to study the control codes in the simplest case, the case of a one-dimensional heat equation. Then we are going to generalize the result for the one-dimensional heat equation for general, for general spectrum, which are complex and whose term do not condensate. In a third section, we are going to work with, in general, with generators, with complex spectrum, but in this case, the eigenvalues could condensate, and this will be our main result. And to finalize, we are going to apply this result into situation for two parabolic systems. Okay, let us start with the simplest case, the one-dimensional heat equation. Well, to this end, we are going to consider a fixed final time t positive, and we consider the heat equation in the one-dimensional case in the interval 0 pi with a control on the point x equal to 0. This is a boundary control, and we act by means of the Dirichlet condition of this equation. Y0 is the initial datum, and V is the scalar control. I remind you that in this case, system 1 is not controllable at time t if for any initial datum is 0, there is a control V in L2 such that the corresponding solution to this problem satisfies Y at time capital T equal to 0. We want to drive our system from Y0 at time T equal to 0 to 0 at time T equal to capital T. And to this end, we are going to act on the condition at the point equal to 0. Well, it is very well known that this system is null controllable. We have this theorem. System 1 is null controllable at time t for any positive time. Well, with this result, in particular, we can work with this set, the set C of t of y0, which is just the control V in L2, for which the solution of this problem is equal to 0. And the result says that this set is different from the empty set. Then we can define the control cost for this system as at time t. And this control cost is given by this quantity is the supremum, when the initial datum, the norm of the initial datum is equal to 1, and the infimum when V is in set T of Y0 of the L2 norm of the control. Well, we know also the behavior of this quantity with respect T when T goes to 0, and this is the new result. There exists 3 positive constants such that this control cost behaves as an exponential of C over T. And this is valid for any t less than t naught. Okay, this is the behavior of the control cost. And if you want, I'm going to try to explain the proof in this for this inequality, the estimate from above. And the main ingredient is the moment method, the Fattorini-Russell method. In order to apply this method, we need two elements. First, we have to know the spectrum of the operator, in this case, for the spectrum of the Laplacian, in this case, k squared, very easy. And also, we have to know that the eigenfunction associated to these eigenvalues is an orthogonal basis of H10, of L2, orthonormal in L2, and orthogonal in H01. Observe that with these two elements, it is possible to give an explicit solution of this problem 1 as a Fourier series. Then we have an expression, if you want. We impose the condition y of capital T equal to 0, and then it's not too difficult to see that the condition y of t equal to 0 is equivalent to this problem. We have y of t equal to 0 if and only if there exists a control V in L2 such that we have this equality for any k. Or if you want, if and only if there is a V in L2 such that we have this problem. This is the moment problem associated to our null controllability result. And if you want, we can analyze the different elements in these equalities. We have, we try to construct a control V such that the scalar product of V times the exponential, the scalar product in L2 of 0t is prescribed, is equal to this quantity. Well, in this quantity, if you want, we have three elements. The first one comes from the action of the control. This is typically, this term comes from the boundary controllability problem, the boundary control. This is the contribution of the initial data. And we have this exponential, this negative exponential, because lambda k is equal to k squared. Then our objective is to prove this if there is a control V such that we have this equality. Well, summarizing, system 1 is null controllable at time t if and only if we can, for any initial data, we can find a control V such that we have this property V time this exponential is prescribed equal to this quantity. And here Ck is the contribution of the initial data, and this quantity is more or less nice because this series is convergent and this quantity could be bounded by C times the norm of square of the initial data. Okay, let us introduce a new definition, the orthogonal family. Then, given lambda k, in general, a complex sequence and a given time t, we say that the family of function qk in L2 is a bi-orthogonal family to the complex exponential if we have this property. The scalar product of my exponential and the element of the bi-orthogonal family is equal to delta kn, the Kronecker delta. Observe that if this family exists, then we have a formal solution of our problem. It is very easy to verify that V equal to this quantity solves, in this case, this problem. Then we have a candidate for a solution of our problem. Then we have a candidate as a solution of our null controllability result. Then we have to question, there exists in general, there exists a bi-orthogonal family associated to this sequence? And the second one, okay, if this family exists, we have a candidate, but this candidate is in L2, that is to say, we have convergence in L2 of this series. Well, this question is related to the behavior of the norm of Qk. For the existence, well, in our case, lambda k is k squared. And then this implies that the series is convergent. And then we deduce that the exponential in L2 is minimal. If you want, is linearly independent. And this minimality result is equivalent to the existence of a orthogonal family. Then we can conclude that if lambda k is an increasing sequence satisfying this property, then the exponential admits at the orthogonal family QK in L2. Then we have, in general, this result is general in some situation, not only for lambda k equal to k squared. Now, it is possible to obtain explicit estimate of the biorthogonal family with respect to k and t. The answer is yes. Assume now that lambda k behaves like this quantity is equal to a times k plus omega squared plus some quantity which is bounded, and lambda k different from lambda n for every k different from n. Then the exponential admits that the orthogonal family QK in L2, and in fact we can prove a stronger property. In this case, we can prove that the norm of QK in L2 is bounded this way. Is bounded is equal, is less than or equal to c exponential c square root of lambda k times exponential of c over t. Okay, we have a system. We have also an estimate from above of the norm of QK. Then we can solve our controllability problem. This is the moment problem, which was equivalent to the null controllability problem. We have a candidate. This is the candidate for solving our null controllability problem. Observe that we have here an estimate of QK. Then we can prove that the series is absolutely convergent. In fact, if we take here norm in L2 of this term, and we apply the previous inequality, we obtain this inequality. Recall that CK was very nice, a quantity very nice. We can apply here the Cauchy's bar inequality, and we obtain this inequality. Here we have two terms. This term is very small, and this could be very large. But in any case, we can apply here the Young inequality, and then this way, and then we can bound this series by this quantity, the series exponential minus lambda kt. The series is, of course, convergent. We can do this. We can calculate, and we obtain this quantity. Then we have solved the null controllability problem, and in fact, we have an estimate of the control V. The control V is bounded like this. Then we obtain in this case the proof of this inequality for the control cos. The control cos is bounded by this quantity. Okay, the proof is a little technical, but in any case, we use for the proof we must use two facts. The first thing is that, well, lambda k is an increasing sequence, and lambda k, the square root of lambda k behaves like k plus something which is bounded. This is equivalent to say that the counting function, which is this quantity, is the cardinal of elements of lambda k which are less than or equal to R. In this case, if this counting function must satisfy this inequality for a given alpha. And we use a second element, the gap condition. the sequence must satisfy this inequality. Lambda k minus lambda n must be greater than or equal to a constant, a positive constant, time k squared minus n squared. Okay, I'm going to do three generalizations. In the first generalization, we are going to assume to work with complex sequences. Also, we are going to work with sequences which in general do not satisfy this condition. Then, with the sequences where the gap condition fails. But in any case, we have separation. This infimum is positive. In a third generalization, we are going to work with sequences for which we have condensation. This infimum could be 0. Okay, let us start with the first generalization. To this end, we are going to consider the first non-scalar system. We are going to consider a 2 times 2 linear reaction diffusion. Very, very simple. It's just two coupled equations, two heat equations. Y has two components, Y1 and Y2. And these two equations are coupled by means of this coupling matrix, A equal to 0, 1, minus 1, 0. We have a boundary control, but in this case, our boundary control is an scalar. V is in L2, and the vector and the control vector is equal to 1, 0. Then here we have two equations, and we have only one L2 control, and we want to control the two equations. We want to derive the solution, Y1 and Y2, at time t equal to 0. Okay, observe that the first equation is not directly controlled. The first equation is controlled indirectly thanks to this coupling term, Y2. Okay, in this case, we have the same elements as before. We know the spectrum, in this case, of our vectorial generator. In this case, the spectrum is equal to n squared plus and minus I. This is a complex sequence, lambda k in general. And we have also a risk basis, in this case, of h minus 1. And the element of this basis are eigenfunction of our operator. Okay, observe that in this case, the gap condition fails, because we can take here, for example, a term, the term 2n minus 1 and the term 2n, and it is clear that this infimum is equal to 0. But in any case, we have separation. This infimum is positive. Then the gap condition failed, but in any case, we have separation. We have no condensation of the eigenvalues. Okay, if you want, the null controllability problem can be written as a moment problem, and this is the moment problem. We have some coefficient. This coefficient contains the information of the initial data, and the problem is to find a control V in L2 such that the integral in L2 of 0t with values in C, well, the scalar product is prescribed and is equal to this quantity. And here the eigenvalues are given by this expression. Well, it is possible to solve this moment problem. Well, the answer is yes, because our sequence satisfies this assumption. The eigenvalues are pairwise different. This series is convergent, and the real part of our eigenvalues is greater than or equal to a quantity delta, a positive constant delta, times the modulus of lambda k. With this condition, we can prove also that the exponential is minimal in L2 of 0t with values in C. And this minimality property is, again, equivalent to the existence of a B-orthogonal family. In this case, Qk in L2 of 0t with value in C. Here you have two references for the proof of this result. Then we have a family, B-orthogonal family. We have a candidate for a solution of our controllability problem. Well, this is our moment problem, and this is our candidate. V equal to this quantity is a candidate to this problem. And the question is now V, as before, V belongs to L2. This is equivalent to see this if this series is converging in L2. And in general, the answer is not. In general, this series is not converging. Or if you want, T must be large enough. We will see this in a few minutes. Okay. And now it is possible to obtain estimates of the norm of the family QK, of the norm of our B-orthogonal family. The answer is yes. To this sense, we are going to assume this hypothesis. We have lambda k, which is a sequence, a complex sequence in general, pairwise different, whose elements are pairwise different. The real part of this series of this sequence is positive, and the imaginary part is not too large. The imaginary part is bounded by beta positive or equal to 0 times the square root of the real part of lambda k. Observe that we add a gap condition, but not for any element. We add that lambda k minus lambda n is greater than or equal to rho k squared minus n squared, but this inequality is only valid if k minus n is greater than or equal to a q positive. But we add an assumption on the condensation. We have no condensation. Lambda k minus lambda n is the infimum is strictly positive. Then any lambda k has around it a finite number of elements which possibly do not satisfy the gap condition. But in any case, we have separation. Okay, we have a third assumption is the same as before. The counting function must satisfy more or less the same property. Okay, with this element, it is possible to prove this theorem to resist tau 0 and two constant, tau 0 and c, such that for any t less than tau 0, we have the same estimates of qk, the norm of qk, the same estimate as before. C exponential of c square root the lambda k of lambda k exponential of c over t. Well, this result is proof in this paper. Observe that we have the same estimate. Then we have our candidate and the same proof as before, as the same proof as for the heat equation provides this inequality. And then this inequality implies the control cost, the estimate of the control cost. Then we can conclude that for our problem is null controllable at any time t, positive t, and there is tau 0 and a constant c0 positive, such that the behavior of curve of t is like for the heat equation. Okay. It is important to say that if our sequence satisfies this assumption, but we have condensation, this infimum is equal to 0. In this case, the corresponding null controllability problem develops a minimal time. That is to say that there is a time t0, which could be equal to 0 or infinity, such that the system is not null controllable if t is less than t0, and it is if t is greater than t0. Okay, then we have to take into account that this infimum, if this infimum is equal to 0, we have a minimum alpha. This result is proved in this paper. Okay, let us now study the general case. To this end, we are going to consider a generator of a C0 semigroup of contraction on a complex Hilbert space, and the spectrum is given by lambda k. Lambda k are the eigenvalues, which are in this case complex and satisfied that are different, are pairwise different. Lambda k is different from lambda n for k different from n. And we are going to assume that the corresponding eigenfunction forms a raised basis on H. Well, we are going to assume that the spectrum satisfies this assumption. The series is convergent and the real path is bounded from below with for this quantity delta is positive, the modulus of lambda k. With this assumption, we can prove this result. Given t, the exponential admits a B orthogonal family, QK, in L2, and this family satisfies this property. For any epsilon, there are two constants which depend on epsilon and on t, positive, such that the norm of QK is bounded this way. We have an estimate from below and from above. Well, here we have the constant. For example, here the constant which depends on epsilon and t. We have an exponential of epsilon, real power of lambda k, but we have 1 over a prime of lambda k, this quantity. E is the interpolating function which is given by this equality, and a prime is given by this quantity. Then we have here the modulus of this quantity, a prime of lambda k. And well, it is easy to see that this quantity could be very, very small, because here we have the differences lambda g squared minus lambda k squared. And if we have a condensation, if we have term which can approach, in this case, this quantity could be very, very large. Very, very small. And then 1 over this modulus could be very, very large. Then it is important to measure this quantity, to measure 1 over a prime of lambda k, the modulus of a prime of lambda k. Well, this could be measured with the head of the index of condensation of this series, which is defined by this quantity, C of lambda, is the limb sub of the minus the logarithm of this quantity over the real part of lambda k. This is always greater than or equal to 0 and could be plus infinity. Well, this result is proved in this paper. Well, observe that these two quantities, C1 epsilon and C2 epsilon, depend on epsilon, and also on t. This depends on t. But the dependence of this constant with respect to t is was not studied in this paper, because in order to prove this inequality, the author applied a contradiction argument. They proved this result for t equal to infinity, and in order to prove the result in L2 of 0t, the author used a contradiction argument. Then it is not possible to know the dependence of these constants with respect to t. And in our analysis, this is very, very important. Okay, We have a controllability problem. This controllability problem is equivalent to this abstract moment problem. And here we have a candidate. Sorry, here, well, here I make an error. Okay, this is Q. Sorry, this is, yes, this is Q. Well, this is Q, and in any case, we have a candidate of our problem, and in this candidate we have this QK, and this QK could be very, very large. We can measure this quantity, and we can prove this theorem. If T is greater than the index of condensation, in this case, this problem has a solution. And this is equivalent to a positive null controllability result. If T is less than this quantity, in this case, there exists a coefficient C, Ck, for which this problem has no solution. Then this provides a negative null controllability result at time T. Okay, it is possible to calculate the control cost when T is greater than this index of condensation. If you want, it is possible to provide explicit estimate of this norm with respect to T and K. Okay, the answer is yes. To this sense, let us assume that we have our sequence, and this sequence satisfies that the element of this sequence are pairwise different, and we are going to add some assumption. The first one is the same as before. The real part is positive, and the imaginary part is not too large. The second one is a condition, a gap condition, but only for some element. The elements which satisfy K minus N greater than or equal to Q. But in this case, we do not assume any condition for this infimum. This infimum could be equal to 0. Then we can have a minimal time. Well, we have a third condition, which is a little more general than before, because the counting function now is bounded from below with a coefficient P2, from above with a coefficient P2, and from below with a coefficient P1. We have more or less the same assumption as before, except this one. In this case, this quantity could be equal to 0, and we can have minimal sign of controllability for our system. Okay. Well, the previous estimates in particular implies that this series is convergent and the real part is bounded from below, the real part of lambda k is bounded from below by this quantity delta modulus of lambda k. Then the exponential, we can assure that the exponential has a minimal, and admit at the orthogonal family. Then we have a minimal sign. Then we can solve our problem if T is large enough. But it is possible to provide an estimate of QK. Well, this is our main result. Under the previous condition, there is a constant, a positive constant, such that for any T, there exists a B-orthogonal family QK in L2, B-orthogonal family, of course, to this exponential, this complex exponential in L2, such that the norm of QK is bounded, the norm in L2 is bounded by this quantity, where PK is the product of any element N which satisfies that K minus N is less than Q. Here we have PK, and here we have PK minus 1. If you want, we can analyze a little this inequality. We have a first part, we have a first part, this part, which is the same as for the heat equation. There is no novelty in this part. The novelty comes here. There is this element, pk minus 1, where pKs measure the difference of lambda k minus lambda n for the elements which could condensate with lambda k, the elements which are around lambda k. pK may be very, very small, and of course, pK minus 1 may be very, very large. In fact, we can prove that this inequality is optimal with respect to pK minus 1 in some situation. In particular, if we assume that there is a nu for which we have this new inequality, lambda k minus lambda n is bounded by n times k squared minus n squared. In this case, we can prove that any bi-orthogonal family Sk to this exponential satisfy this inequality. In this inequality, we have some terms, but observe that we have pk minus 1. Then, and pk minus 1, if you want, in this term, we have the information about the possible condensation of our sequence. Okay, the proof is very, very technical. I prefer not to go to the detail. This result is proved in this paper, a paper with Lydia Wiley. Well, only two remarks. The first one is if we have a separation, an assumption of separation of our element of our sequence lambda k, if lambda k minus lambda n is greater than or equal to gamma positive, in this case, for any k different from n, in this case, we have no condensation, and it's very easy to see that pk minus 1 is bounded by a new constant, which depends on gamma and q. Then observe that this term disappears and could be, if you want, integrated in here in C0, and we obtain the same result as in this paper. Then this result generalizes the previous one. The second remark is that in this paper we obtain an explicit dependence of the constant C0 and C1 with respect to the parameter which intervenes in our assumption, beta, rho, q, p1, p2, and alpha. Okay, I prefer to finalize with two generalizations. We are going to apply this result to two different situations. In the first situation, we are going to consider a new reaction diffusion problem. We have two coupled heat equations. Y has two components, y1 and y2. Here we have a diffusion. The diffusion D is a diagonal matrix, 1D, D is positive and is given. Here we have the coupling term, y0, which is equal to 0, 1, 0, 0. And here we have the control vector, B is equal to 0, 1. Then, as before, we want to control two equations, but the control V is a scalar in this case, and the control V acts only on the second equation. The first equation is indirectly controlled by means of this coefficient. Okay, is this problem null or approximate controllable at time t for a given t? Well, this depends on D. We have two different situations. In the first case, if D is equal to 1, and if we call Il1 equal to our operator minus D Laplacian plus A0, well, in this case, if D is equal to 1, the diffusion matrix is equal to identity, and in this case, the spectrum is just like the spectrum of the heat equation, k squared. But if this is different from 1, in this case, the spectrum is given by n squared, then dn squared. This is a positive increase. This this sequence can be written as a positive increasing sequence, called in this case lambda K1, and observe that in general, well, we can have condensation. Let us analyze the case d equal to 1 because it's easier. Well, if d is equal to 1, in this case, system 3, this system is approximate and uncontrollable at any time t. And moreover, we can prove the existence of three positive constants such that the control cause is bounded as before. Is bounded like in the case of the heat equation, the one-dimensional heat equation. Well, the problem, the null controllability result can be found in these two papers, and the control cause, these two inequality can be found. The proof of these two inequality can be found in this paper. Okay. What happened now if d is different from 1? In this case, it's very easy also to prove this approximate controllability result. If d is different from 1, system 3 is approximate controllable at time t, if and only if the element of the eigenvalue, are pairwise different. Lambda k1 is different from lambda n1 for any kn, k different from n. And this is equivalent to this condition, and this condition is equivalent to this, is equivalent to this condition. The square root of d must be irrational. Then we have the the approximate controllability. Okay, now if we have this, if the square root of d is an irrational, it is possible to prove a null controllability result. The answer is yes. Well, let us assume in this case that the square root of d is an irrational. In this case, we can prove the null controllability at time t, but with a minimal time. Observe that in this case, this is our spectrum. The sequence lambda t, of course, satisfies this condition. This condition implies, of course, that the existence of the orthogonal family, and also a controllability result with a minimal time. And this minimal time is the condensation index associated to this quantity, to this sequence, sorry. Observe that in general, this condition fails in general. We can have this quantity, the infimum of this quantity could be equal to 0. Then the null control, we have condensation, then we have in general a minimal time of controllability. But in any case, we can compute the minimal time, which is given by the condensation index associated of our sequence, and we have a null controllability result. If we take T0 equal to this condensation index, well, we have that our system is null controllable if T is greater than T0, and is not null controllable if T is less than this quantity. Well, this result was obtained in this paper. Okay, but it is possible to see the control cause associated to this problem when we have a positive null controllability result. Well, to this end, let us see if this assumption holds in our case. Well, this is very easy. We have this proposition. If we take P equal to 1 plus 1 over the square root of d, we have first, the eigenvalues are positive. 2, we have the gap condition for any element k and n, which satisfy k minus n greater than or equal to 2. We have possible two elements which can accumulate, which can approach. But in general, this inequality, except for these two elements, this inequality is valid. We have also the same property with the counting function, and we have this additional condition. Then we can apply the main results, and we obtain this corollary. There exists a constant C0 such that for any positive time there is a orthogonal family Qk, and the norm of Qk is bounded as before. In this case, observe that pk minus 1, pk is given by this problem. Observe that we have two elements which can approximate. Q is equal to 2. In addition, any orthogonal families Sk is bounded from below like this quantity. And here we have the same element. Well, observe that pk must be, we can have element which approach, and this quantity could be very, very small, and then pk minus 1 could be very, very large. We are going to study a case in which pk and a case in which we have condensation, but this element is nice with respect to this exponential. This is the case in which a square root of d is an algebraic irrational number of our degree L. In this case, we can prove that lambda k1 minus lambda k1 is greater than or equal to a positive constant over kl minus 2. Then this quantity could be very small, but not sufficiently small. Well, this result used in order to prove this result, or this result is a consequence of the Liouville theorem of Diophantine approximation. If nu is an algebraic irrational number of degree L, we know the existence of a positive constant for which we have this nu minus p over q is greater than c over q to the power L for every integer pq on set q positive. And this result is also in general is valid for irrational numbers with finite Liouville constant. Well, this is not important. The important thing is that in this case, this quantity must be very, very small, but nice in any case. In fact, if L is equal to 2, is square root of this a quadratic algebraic irrational number, one has that our sequence does not condensate. We have the existence of sigma such that lambda k1 minus lambda n1 is greater than or equal to sigma for k different from n. And in fact, it is possible to characterize the coefficient d for which this inequality is valid. Okay, the quantity pk minus 1 is not too bad. Then we can, in this case, for algebraic irrational numbers, we can prove the same result as in the case of the one-dimensional heat equation. We have condensation, but the norm is more or less good. Okay, and we have in this case, as a corollary, we have that in this case, in the case of a scale root of the algebraic irrational number of degree L, we have that this system is controllable for any t positive. In this case, the minimal time is equal to 0, and we have the same behavior or the control cost. The control cost behaves as an exponential c over t. Well, it is possible to find some example where this control cost has a more explosive behavior when t goes to 0. Well, the answer is yes, and this is my final application. In this case, we are going to consider again a 2x2 system. Okay. In this case, we have a diffusion and a diffusion matrix equal to identity. Y has two components again, y1 and y2. And the novelty here is that we have a coupling which depends on a function a of x. A is a function in L2, and we are going to assume that the mean of this function is equal to 0. And we have the same as before. We have only a control. V is in L2. We want to control two equations by means of a unique control V. In this case, A1, the coupling matrix is equal to 0, 0, 0, 1, and the control vector is equal to 1, 1. Okay. This problem is null or approximate controllable at time t. Okay, we analyze in this case the spectrum as before. The spectrum is given by this sequence n squared plus beta n. And well, this is a new increasing, this sequence can be written as an increasing, a positive and increasing sequence, lambda k2, and here beta n is a new sequence which lives in L2, and this is a consequence of this assumption. The mean of E is equal to 0. Then beta k goes to 0 when k goes to infinity. Then, of course, this infimum is equal to the infimum of beta k, and then is equal to 0. Then we have condensation, and of course, the gap condition fails. Then typically here we have condensation. In any case, we can prove again an approximate controllability result. This problem is approximately controllable at time t if and only if we have a new condition, lambda k2, the elements of the spectrum are pairwise different. This is to say that k squared is different from n squared plus beta n. Okay. Then it is possible to prove now a null controllability result. Yes, the answer is yes, because the spectrum satisfies the condition as before. This series is convergent, and the real part, of course, is greater than or equal to this quantity, because delta in this case is 0. We have a real sequence. Then we have a minimal time. And we have a null controllability result if t is greater than the condensation index associated to our sequence. Then we have this corollary. Under the previous condition, the minimal time is given by the condensation index associated to our sequence, and we have a null controllability result if t is greater than this time, and if t is less than this time, the problem is not null controllable at time t. This result is proved in this paper. Okay, in this case, the condensation index is very easy to be compute. In this case, the condensation index is given by this quantity. T0 of A is the lim sup of the minus logarithm of the modulus of beta k over k squared. And this quantity is in between 0 and infinity, and could be 0 and also infinity. Recall that beta k is in L2. Then beta k goes to 0 when k goes to infinity. Okay, now let's see if our sequence satisfies the previous condition, and the answer is yes. We have that the sequence is positive. We have the gap condition f set may be 2 elements if k minus n is greater than or equal to 2. We have this condition for the counting function, and we have this additional condition. Then we can apply the main result and obtain this corollary, the same as before. There exists a constant, two constants, such that for any t, we have an estimate of the norm of qk with the same structure. The element which come, if you want, from the heat equation, and the condensation pk minus 1. And we have also that this quantity is optimal with respect to pk, because any bi-orthogonal family satisfies this condition. In this case, pk goes to 0, and in fact, we can prove that the elements p for the even element and the odd element is bounded this way. Then observe that beta k is in L2. Then these two quantities go to 0, and then pk minus 1 goes to infinity. And the contribution of this quantity could be very, very explosive. Let's see this contribution in an example. To this end, I'm going we are going to see this lemma. Given gamma, we can prove that there exists a coefficient A with mean equal to 0, such that with this coefficient, the spectrum of our problem is given to n squared plus the exponential of minus n to the power 2 gamma. And this is this is now our spectrum. Observe that in this case, beta n is equal to the exponential of minus n to the power 2 gamma. Then the contribution of the condensation is very strong. The minimal time in this case, thanks to the fact that gamma is in between 0 and 1, the minimal time is 0. Then our system is null controllable for any t. But observe in the previous inequality, the contribution on this quantity is very, very large. We can prove that the sequence of the orthogonal family is bounded this way, and observe that this contribution could be explosive. Well, if now we analyze the null controllability problem, in this case, this contribution gives a new term for the control cost. We can prove, in this case, for this particular coefficient A, that our system is null controllable for any time t, and there is 3 positive constants which are independent of gamma, such that the control cost is bounded by these 2 quantities, the exponential of c over t, well, this is as before, but observe that we have here a new term, and this term comes from the condensation. We have the exponential of c over t to the power gamma over n minus gamma. And the contribution is explosive when gamma goes to 1. Well, it is not difficult that if gamma is less than or equal to 1/2, in this case, the important term is c over t. And then in this case, the control cost is like in the case of the one-dimensional heat equation. But if gamma is greater than 1/2, in this case, the control cost has this behavior. Is the exponential of c over this quantity t to the power gamma over 1 minus gamma. And observe that if gamma goes to 1, this quantity has blow-ups when gamma goes to 1. And this is normal, because if we take gamma equal to 1, in this case, our system is null controllable only if t is greater than 1. And of course, is not null controllable if t is less than 1. Then this is more or less normal. Okay, if you want, in order to finalize, I have no time. No, well, only two words. in the case in which we have two independent control, we have the same number of control than equation. In this case, we have the same control cost as in the case of the heat equation, and this result is valid in any dimension and for any coefficient. Okay, and sorry, I'm very sorry. Here you have well, the paper I used in my talk, and thank you for your attention.
Thank you, Manolo.
Sorry.
Very nice talk, but okay, we are a little late, but maybe somebody has a question, comment. If you have a question, please open your microphone. That's okay. If not, okay, I have a question. No, Sylvain, please.
Yeah, so if I may, on the negative part of your results, so I think it was in the first part of your talk, you were saying that if the time is smaller than the condensation index, then there are some initial datum that cannot be controlled to zero. But do we have an idea of what are the initial data which can be steered to zero?
In some situations, yes. For example, in the case of the last example, if you want, you have two equations. Imagine you take an initial data for which the second equation, the equation which is not directly controlled, is zero, for example. In this case, well, you have null control. In this case, you have your moment problem, if you want, is decoupled, and you are not able to see the condensation effect. In the first case, it's not too easy.
Yes, but I mean, it seems to be specific to the model you are considering. So, for instance, I remember this work by Miku and Zuazua on the harmonic heat equation on R. So the spectrum is simply the integers, and then you cannot control any initial datum in L2 to zero with a strong non-controllability result, and it seems to be related only to the spectrum, right? So they are seeing that on the spectrum. So I wonder if there are some similar cases or not.
The character of this problem is different, because in that problem, in the problem of Miku and Suasua, I remember that the problem is that you have the control is supported. You have to have a control with support uniformly in your unbounded domain.
Can say something like that, but I mean, this is a self-adjoint operator. I think for the eigenvectors, these are the Hermite functions, so they have the good property. So I think it's really related to the condensation index, no?
Maybe. In their case, well, I don't know.
I think you have also a similar result for the heat equation with the fractional heat equation with parameter 1/2. So the spectrum is again the integer, and there you have some rather strong non-controllability result, if I remember correctly.
Yes, because in some way you have a very important assumption. Your series and over lambda k must be convergent. And then the first case in which this assumption is not valid is just for the case of the Laplacian to the power 1/2. In this case, this series, the exponential are linearly independent, if you want. You lose the minimality property.
Ah, okay. Mm-hmm.
Then the situation, I think the situation is different. Is different. And in the unbounded problem, I think the problem is the same. In some way, you lose your parabolicity in some sense.
Okay.
Okay.
Thank you.
Another question or comment?
Please, I have a question.
Yes, please.
Yes, thank you very much. I have a question in the second part, the second application.
Mm-hmm.
You took the operator B. My question is, what happens if we take just one control, a control on one component, not
You mean in the second problem? The sound is
yeah.
No, in the second problem, if you take, wait a moment. If in the second problem you take B equal to 1,
Yeah,
0,
1, 0.
in this case, the problem is not coupled. If you take B equal to 0, 1, the first equation is
Okay.
free. It's free.
Yeah.
You have, this is necessary, your control B, the components of your control B. For example, I take 1, 1.
The coupling there. Yeah. Okay.
You have to take B equal to B1, B2, but B1 and B2 must be different from 0. If not, your system is not controllable. You can take here any quantity, B1, B2, but these quantities have to be different from 0. B1 times B2 must be different from 0. Okay, this is necessary. Okay.
Okay. Okay, I have also a comment on the domain of L2, the operator L2, H10 or H1?
The name?
The operator L2.
Yes, it's H10, H2,
Yes.
section H10, yes. Yes, A belongs to L2, and we have in the dimension is 1. We work in 0 pi.
Okay.
Okay.
Thank you very much.
You're welcome.
Thank you. Any other comment or question? I have a question. When you estimate the cost of the control, but you have a minimal time of controllability, you don't have a dependence on this minimal time for the cost?
This minimal time depends on the cost.
Yes, the minimal time depends on the condensation, but the cost.
Sorry, the cost depends on this minimal time.
Okay.
But well, this is a work in progress, and because in this example I only consider the case in which the minimal time is equal to 0.
It's equal to 0. Okay.
The result is general.
Okay.
The main result is general.
So you have something like capital T minus capital T0, something like that.
Yes, but you can have any behavior of the control cost. Okay. And this is associated to the way of this. Wait a moment. To the control
condensation.
Code. Yes, the condensation. This depends on these limits. Well, I don't know where this. Okay, here. This is only 2.
Yes. Yes.
this means that there is a subsequence. Well, this the control curve is associated to the way of this limit is equal to C of lambda.
Okay.
Okay, and you can have any behavior of this control cost.
So we can conclude that we don't have a behavior as in the paper of Pierre Lissy.
I think that the behavior, more or less, we can repeat the same argument, Asia. Asia, no?
Yes, it's Asia. You don't see me, okay.
We can repeat the same arguments.
The same as.
I think I'm not completely sure.
The same as what?
The same argument at Pierre Lissy.
Okay, yes, I agree. Yes, okay.
Okay.
And but in your answer, the domain of L2 is not H10 because because there is the control, the domain of the adjoint. But
yes.
Okay, because the control is exerted at the boundary. No.
No.
It depends on how you write it. Yes.
Okay, for me the L2 is with homogeneous boundary condition.
Okay. I got it.
Well,
thank you.
If there is not another comment or question, let's thank again our speaker.
Thank you.
And see you next month. So thank you very much.
Gracias. Merci.
Thank you.